and you can take a bunch of panos in your house, and it'll link it all together and create like a virtual home tour for real estate listings. And during the pandemic, it's taken off massively. They have some public information. They have some slide that shared. It was like it's gone up something like 100% since March in terms of usage, which is pretty impressive. Yeah, I can share that link to their talk. It's from Singbing Kong, is the distinguished scientist there. He's a fairly well-known name in 3D reconstruction. He gave this talk and talked about how they were doing.
Yeah, for sure. Share it, please. I also wanted.
Yeah, no worries. And I'm going to see if I can get the screen share set back up so we can get going. Okay, cool. Hi, everybody. Welcome. Yeah, welcome to today's talk. As Peter said, my name is Marc Eder, and recently I completed my PhD at the University of North Carolina at Chapel Hill here in the US. And during my time there, I was advised by Dr. Jan Michael Fromm, and I worked on a variety of problems between 3D reconstruction and deep learning and a lot of things in between. For the last few years of my degree and ultimately for my dissertation, I most intensely focused on this emerging topic of 360 computer vision. And this is what the subject of my talk is going to be today. The last few years have seen the emergence of technologies and devices that allow us to capture the entirety of our surroundings with a single click. And so now the question is, what do we need to do in order to leverage these new technologies if we want to maximize computer vision's field of view? So today's talk is going to be broken down as follows. First, I'm going to kind of define the topic of 360 computer vision, and I'm going to highlight some applications of 360 images and identify how computer vision can play a role. We were chatting a little bit about this before we started off. But so then I'm going to talk, I'll introduce the spherical distortion problem, and why it's not so simple to just take our off-the-shelf, I hope this isn't on a timer. We will introduce, excuse me, yes. And then after that, I'm going to present my 3 guiding principles that should underpin any solution to the 360 computer vision problem. I'll talk a little bit about why that's the case, and we'll look at some selected relevant work through the lens of these 3 guiding principles. Subsequently, I'm going to talk about the icosahedron. This is this like magical representation that uses this polyhedron, and it has driven some of the biggest advances in deep learning for 360 vision. And then finally, the bulk of the second half really will be talking about my recent work in this space, which is the tangent image representation. And this I introduced at a paper at CVPR this year. This representation captures the useful properties of the icosahedron, but uses a more effective representation for kind of our existing computer vision algorithms and paradigm. So I plan this to run about an hour, might go a little over, but it should keep plenty of time for questions at the end. Okay, so let's start out defining what I mean when I talk about 360 computer vision. A broad but appropriate definition is performing inference, estimation, and modeling tasks using images that capture a scene with a 180 degree by 360 degree field of view. You know what this is? I have timing set up from a previous slides, and I've reused some slides here. So this might get a little annoying, I hope not. In any case, for the sake of simplicity, I'm going to simply refer to 180 by 360 as a 360 field of view. If we want it to be 100% precise, we would say a 4 pi steradian field of view. This is a way of like looking at spherical triangles and measuring that. But 360 should suffice. So now this definition is very broad, as I said, but it encompasses deep and shallow learning techniques, image processing operations, and 3D modeling and photogrammetric tasks. As 360 data acquisition has become easier thanks to the emergence of commodity 360 cameras and high quality smartphone panel stitching and things like that, the number of applications has grown considerably. One of the most widespread uses is virtual tourism. It's actually particularly great for times like now when everyone's stuck at home in quarantine. So you know, with these 360 videos, we can magically whisk away to the African savannah, or virtually explore London. Or you know, maybe you're feeling really adventurous, you can take a helicopter ride over Victoria Falls. All of these are ways that we kind of are using 360 already. These are just YouTube videos right now, and you can set them up with any sort of VR viewer. Another useful application of 360 vision is navigation. Google's Street View service was actually one of the first widespread products to leverage 360 images. And this can be used to allow users to navigate and explore places on the map as though they were there in person. I've actually used this for navigation purposes. You know, I want to know which side of the street something is on, where something is. It actually becomes quite a useful ability to turn around and feel immersed. E-commerce is also growing as a platform for 360 as well. We were talking a little about this earlier. Zillow's 3D home product, which is what you see here. This allows prospective home buyers in the US and parts of Canada to explore other homes on the market from the comforts of their computer screen. Now, due to COVID, this product's actually seen massive growth on their platform, and it's really starting to bolster the value of 360 images as a useful tool for immersive exploration. Another fast-growing application is remote inspection and documentation. I know of at least 5 different small companies and startups, like OpenSpace, which is the one shown here, that are leveraging 360 images for construction management, for remote management platforms for construction and other industrial projects. And again, as remote work is becoming more normalized by COVID and you know, just a general global pandemic, it's likely that applications like this are poised to grow even further. So there are many other applications as well. You know, medical imaging applications. There are some ultra-wide field of view endoscopies that have been released, as well as some kind of innovative ideas. There's one called the CapsoCam, which is a little capsule that you swallow, and it takes pictures, 360-degree field of view, as it passes through your system. But these new technologies can expand how much a physician is able to see. There are also robotics and autonomous vehicle applications. Think about the safety features that can and are being built using a 360-degree field of view. Then there are other miscellaneous applications as well. Things like 360 Instagram filters, or auto tagging features on 360 images if you upload it to social media sites. I don't know, y'all on Facebook, you've probably seen you can upload these 360 panos. Now we need to be able to address them as we would any other 360 image in order to take advantage of the computer vision algorithms that are currently in use on standard images. So with all these really cool, exciting opportunities, the real question is, what's holding us back? And the short answer is spherical distortion. So in this talk, I specifically differentiate 360 computer vision as its own class of problems. And I do this for 2 reasons. One, because 360 images use a very specific camera model, which is based on a sphere. And this requires different considerations than the standard central perspective camera. And because we are using this spherical camera model, we end up with spherical distortion in our resulting images. And many 360 tasks are affected by this unique problem, which, unlike geometric distortion, like the radial or tangential distortion models that you may be familiar with of a standard perspective image, those are functions of the physical lens itself. But spherical distortion is actually a function of the image representation, which makes these problems a little bit different in how we want to address them. So it might help to understand this if we first take a look at the camera model for 360 images. On the left, you see the standard illustration of a central perspective camera. In a central perspective camera, the image is formed via perspective projection. So you can think about rays being cast outwards. Actually might be better to think about rays being cast inwards, but for the sake of this visualization, it's easier to reverse the process. Think about like sampling from a 3D world. But basically, rays can be cast outwards from a center of projection towards the world, and whatever they hit is projected back onto an image plane. How much of the world these images capture is dictated by the camera's field of view in the X and Y directions. And this is going to be a function of the camera's focal length, or the distance from the center of projection to the image plane. Now on the right, we have the 360 camera model. It's a spherical camera. So here we replace this concept of an image plane with that of an image sphere. Our center projection is now the center of the sphere, and rays are cast outwards in all directions with the full 180 by 360 degree field of view, a 4 pi or steradian field of view. Projected onto the inside of the sphere and indexed by spherical coordinates. I like to think of capturing a 360 image as like you're standing in the middle of a snow globe and you're pasting the inside of the glass, excuse me, with the image. In any case, because of this camera model, we also refer to 360 images as a spherical image, as spherical images. Now, because many computer vision algorithms have been designed around the concept of an image plane, we need to first project our spherical image onto a planar representation in order to apply the algorithms. And this operation, this mapping to an image plane, this is what results in the spherical distortion that warps our images in a location-dependent manner, and which results in local deformations that ultimately impede our current computer vision algorithms. So kind of to sum up a little bit on this, the reason that spherical distortion occurs is because we model the spherical camera with a sphere instead of a central perspective image. But the resulting distortion makes it very difficult for us to take our kind of off-the-shelf computer vision algorithms, whether they're convolutional neural networks or a SLAM algorithm, and just directly apply it to this planar representation of a spherical image. Now, let's take a look at the two most popular spherical image representations we use. On the left, you'll see a cube map. And so this is the projection of a sphere onto an inscribing cube. Basically, think about putting a sphere in a box and projecting it onto the inside of the box. It's really popular in graphics because it provides an efficient solution for environment mapping. But in computer vision, we more frequently see the equirectangular image. This image is formed by projecting the sphere onto a cylinder and unraveling it. I like to think about like cutting a line from the North Pole to the South Pole, and then you just like unwrap it and pull it into a rectangle. And the reason this is so popular in vision is because it's a simple rectangular image. So in theory, it looks just like all of our other images. The aspect ratio is 2:1, but beyond that, it's basically the same as everything else. Nevertheless, despite the popularity of these two image representations, these projections distort the spherical content. And this is clearly visible when I superimpose Tissot's indicatrices. These indicatrices are perfect circles of the same size and orientation when they're on the surface of a sphere, like you see rotating on the right here. But when we project these onto the image representations, they deform into ellipses. Now, the change in the area, eccentricity, and rotation of the ellipse is a good indicator, and it actually provides a measure of how much distortion there is at each location. Ideally, we want our planar projection to have perfect, equally sized circles. Unfortunately, this is not the case for these representations. In particular, I want to draw your attention to the strong horizontal distortion near the poles in the top and bottom of the equirectangular image. This results in heavy pixel redundancy, and this will come up later in my talk when we talk a little bit about some experiments. So why is this distortion a problem? Well, for many of those applications we talked about, we want to apply some specific computer vision algorithms, such as we want to be able to localize and identify objects in a scene. Or for autonomous vehicles, we hope that the car can determine where the road ends and a sidewalk begins. So the ability to semantically segment an image, or to instant segment an image, is going to be very important. Now for virtual tours, something like Zillow's 3D Home, we want the user experience to feel natural. This means we need to have a good estimate of the underlying 3D geometry of the scene. Otherwise, we get dizzying effects like you see with the walls and the door here. This is what happens when you have planar objects that are projected onto the surface of a sphere. So currently, many of these tasks are achieved using revolutionary state-of-the-art computer vision algorithms called convolutional neural networks, like you see here. Now, convolutional neural networks are a deep learning tool that stack learnable convolutional filtering operations in sequence to create highly effective predictive models. The issue for us is that they're predicated on a local operation, namely convolution. So if we take this convolutional filter, also known as a kernel, on the left, we can convolve on the image on the right by sliding the filter over the image, and we aggregate local information at each step of the way. So it slides in this sort of sliding window pattern. We aggregate this information. Now, a revolutionary concept with convolutional neural networks has been that rather than having a unique parameter for each pixel, the way we would with a fully connected network, we can share parameters across the image via this filtering operation. Yet this parameter sharing design relies on a concept called translational equivariance. This means that if we were to shift the input image in some way, the output of the filtering operation should shift equivalently. But if we were to look at spherical projections, this is actually not the case. So on the left, I projected that picture of a dog onto a hemisphere at the equator, and then I rendered it to a spherical projection. Now on the right, I've shifted the dog up by 45 degrees of latitude in that projection. Notice how this translation operation has now changed the image. Here's a zoom in on both of those images. As we talked about before, you can clearly see the effects of the location-dependent warping. Now, even if we only focus on on a region of the same size, when convolution is run, we see that the filter on the left image covers. Excuse me. We see that the filter on the left image covers nearly the dog's whole head, while on the right it barely covers half of its nose. With such distortion, we can't expect this filtering operation to have the same output on the shifted image. This is an important observation because it's the translational equivariance requirement.
Mark, quick question about this. That's very interesting. I actually, I didn't think about it when I was examining these algorithms, for example, for automotive self-driving cars. Today they use any way of fixing the spherical distortion or not really in the applications that are being tested and run today? So
that's an interesting question. Some of the stuff like proprietary things, I don't know. I assume they are. I do know that for autonomous driving, one thing I learned actually in that workshop I organized CVPR is that they are trying to address this because this comes up a lot with fisheye cameras, which actually can be modeled as a hemisphere, or often can be modeled as a hemisphere. And they are trying. I know that research is being done to address the spherical distortion for these fisheye cameras, but so they can't really, I see somebody says you can use deformable kernels instead. We'll talk about that. So that is one of the approaches that I know is being used, at least by some organizations. The problem is that deformable kernels don't actually, automotive industry is very cost conscious. Yeah, my information is specifically coming from a company called Valio. They make manufacturers of smart automotive parts. And I know they're working on ways to address this. But yeah, as William Payne, I guess, pointed out, automotive industry is very cost conscious, and they're also very safety critical. So anything that's going to add extra latency into their predictive models or potentially add extra cost, whether it's energy cost or literally just the cost of the device, it's not necessarily being put into practice now. But I know research is being done. Papers have been published. And I know that Waymo, for example, hired a couple of people who had worked on Google's Jump camera, which was a 360 camera. So I have to imagine that they're taking advantage of this in some way. Waymo is a big automotive car manufacturer, or excuse me, big
autonomous vehicle
car startup and based out of the US.
Yeah.
But yeah, so this is a problem. The question really becomes, and we can talk about this maybe a little more at the end, whether this problem is, how big of an impact this problem has. Now, for dense prediction, it turns out, we'll talk about this, the problem is pretty bad. It actually makes a big difference. For localization or classification, it's not as big of a deal necessarily. Localization algorithms are typically built with multi-scale detection. And so oftentimes you will capture the same things at a larger scale than you should. And then for global operations like classification, you are ultimately taking all the pixels into account. So there is a drop off in performance, but it's not nearly as bad as when you're dealing with a dense prediction. So depth estimation and semantic segmentation or instant segmentation, where one pixel being off is an error. And here, this distortion affects pixels quite a bit. Does that answer the question a little?
Yes, for sure. Thank you.
No problem. But yeah, so we were talking about translational equivariance and why this is a problem for convolutional neural networks. But it's actually not just unique to deep learning. So let's say we have this dog, and you have to use your imagination for a second. Just pretend this dog is three-dimensional. So now we have two spherical cameras and we've got some baseline between them. So there's parallax between the views. Now notice that those pink pyramids are visualizing the orientation of the camera. And they're also kind of demonstrating the field of view we're interested in at the moment. Let's say that these cameras produce the images to the left. These are kind of those two images that we had before, but we're now, for the sake of this example, we're pretending there's some parallax between them so we can actually get some geometric depth. So if we want to perform geometric depth estimation, we need to solve what's called the correspondence problem. So if we know the relative poses of the cameras, identifying the pixels in the right view that correspond to the pixels in the left view is equivalent to estimating the depth of the image. And so solving this dense correspondence problem is key for problems of geometric 3D reconstruction. Yet stereo correspondences are found by computing some metric like normalized cross correlation or the sum of square distance or sum of absolute distance. And we do this over some local region of pixels. And these local computations are once again the source of our problem. If we come back to focus on just the areas of interest for a second, we've got our left view, which imaged a dog to the equator, and our right view, which imaged it at 45 degrees latitude on the sphere. Now let's pick a corresponding point between these two views. If we look at a 3x3 pixel region around this point and compute our metric, we're going to have a very noisy outcome because the data within the window on our left is quite different than the data within in the right view. Now, obviously for visualization, the region I'm highlighting is much larger than a true 3x3 pixel region. But it turns out that the content deformation, even locally, has a non-negligible impact on these small local patterns that are key for finding dense correspondences. Now, this is an important problem to solve because these pixel-wise correspondence matching algorithms are the core operations underlying stereo depth estimation, multi-view stereo, and dense SLAM. Now, other tasks like camera calibration or structure for motion seek to find sparse feature correspondences. For these, we don't need every pixel to have a correspondence, so long as we have enough points to estimate relative camera pose or camera intrinsics information. Yet these tasks that use sparse features leverage algorithms that try to identify feature points on the image that are compact, robust, and repeatable. And these key points, as they're called, are then associated with a descriptor, which is a numerical vector. And these descriptors are intended to be somewhat unique to the local patterns around the key point. This is what allows for that same key point to be identified in other views of the scene. We then match these corresponding points by checking some metric between the descriptor vectors. So at a high level, we find our sparse correspondences by looking for key points whose descriptors are most similar. Now, a prominent example of this type of sparse feature key point are SIFT key points. This is arguably one of the biggest advances or like most widely used advances in computer vision in the last few decades. 20-year-old technology, still widespread today. This algorithm, it's scale invariant feature transform. It's extremely widespread today. But often we talk of these algorithms as trying to achieve viewpoint invariance. So what that means is the descriptors don't change as the viewpoint changes. Ideally, if we can achieve that invariance, we should always be able to find the necessary correspondences as long as it's within the field of view of whatever our camera is and it's not occluded. But SIFT and the myriad other features like it, brisk, orb, surf, fast, there's a bunch of them. They're primarily designed to reduce the impact of illumination, content rotation, because with most cameras out there, most prospective cameras, these are the big changes that happen between viewpoints. They're not designed, however, to handle content that's being expanded or contracted so significantly as we see with spherical distortion. So for example, SIFT uses local gradients. So these descriptors are computed based on some local region around the key point. Just like convolutional neural networks and our dense pixel matching algorithms, even our sparse key point detectors are going to be heavily reliant on this local information to compute descriptors. So this corruption of the local information that many of our algorithms rely on has led actually to a performance gap between central perspective and spherical images. Unfortunately, though, it turns out there's nothing we can really do to address this spherical distortion problem. A consequence of Gauss's famous Theorem Egregium is that a sphere is not isometric to a plane. So what this means is that all spherical images will necessarily have some distortion. So therefore, our only option is to accept the presence of distortion and seek ways to mitigate its effect. As we're going to discuss in a minute, there are a few different ways to approach this problem, many of which involve adapting algorithms to spherical data. But the key observation I want to come back to is that our choice of spherical representation is what dictates how much distortion is going to be present. So given this, the argument that I'm going to make is that the best path to a general solution is not by changing every single algorithm, but rather by finding a better spherical representation. So now I arrived at this conclusion by trying to determine a set of heuristics that are kind of common to all vision tasks that our solution needs to satisfy. And this line of thinking has brought me to what I've taken to calling the three guiding principles. That's what it is, the three guiding principles of 360 computer vision. So basically, any solution to the spherical image problem should satisfy three characteristics. We need to address distortion, scale efficiently to high res, and permit the easy transfer of existing algorithms to 360 data. Now, distortion mitigation is necessary for the reasons we've already talked about, the content deformation, translational equivariance, and this performance gap. Efficient scalability is key for 360 images as well. And we're going to discuss this concept when I talk about tangent images later. And then finally, computer vision is not that old of a field, right? It's been around maybe a half a century, but it has been around for about a half a century. We have a half a century of existing work. So any solution for 360 images ought not to reinvent the wheel. It should facilitate the simple transfer of existing algorithms to 360 data. Now, in the next few slides, I'm going to review some of the broad classes of existing research that have looked at the spherical image problem, and we're going to analyze them through the lens of these heuristics. For the sake of time, I'm not going to dive super deeply into all of them, but I'll provide a paper.
Hello, hello. I think it got cut off a bit. Yeah, I think we lost them. Something weird is happening with the internet today on his end, on mine. We'll wait for him to come back. But in the meantime, it's a good chance to ask everybody, where are you from? What are you working on? Oh, Mark is back. Still feel free to send on a chat here. What do you do with computer vision? Where you originated? It's always interesting to know who's with us.
Yeah, am I back?
Yeah, you are. You are.
Okay, and you can see my screen again.
Yeah, we see it.
All right, cool. Where did it cut out?
Just after you said that we need to be able to simply transfer between different algorithms because there's half a century of work already done.
Okay, cool. Thank you. Yeah, so what I was starting to say, basically in the next few slides, I'm going to review some of the broad classes of existing research into the spherical image problem. And we're going to talk about them through the lens of these three principles. For the sake of time, I'm not going to dive super deep into all of them, into like each paper, but after the talk, I'll give a paper list. There's also a QR code to that blog post, and I know Peter said he'll share that as well. If you're really interested, feel free to read the related work chapter of my dissertation, which highlights all of them in some detail, but I'm not going to hold it against you if you choose not to do that.
Mark, if there is a spot where just all these references are in one place, just this, send me a link or something, and I'll also post it on the references. It's much easier to find this way, so why not?
Yeah, I'll do that right after this.
Mm-hmm.
Cool. But yeah, so let's dive into this recent work then. It's kind of possible to group most of it into three categories. The first is convolution reparameterization methods. Then we have learnable transforms, and we have location adaptive convolution. So somebody mentioned earlier, just use a deformable convolution. So that falls into this category. So let's go from left to right here. This first category involves methods that reparameterize the convolution operation in some way. These methods are typically agnostic to the image representation. They focus on the spherical nature of the input signal. And they're often mathematically rigorous and approach it from a really theoretical perspective. More often than not, they approximate convolution. So they use, let's say, spherical harmonic functions or spectral transforms instead of the sliding window convolution that we are familiar with in our convolutional neural networks. If we look at this through our three guiding principles, these actually largely address distortion because they're designed for a spherical signal. Although it is a valid question to ask whether it's appropriate to ignore the discretization effects of an image. Now, these solutions have also been quite efficient and thus scale fairly well, but they're not transferable because we're no longer using this kind of core convolution operation that underlies all of our existing methods. You know, our ResNets, our VGG networks, our, you know, pick your favorite network. So the next category of prior work are methods that seek to learn to transform a network to adapt to distortion. So this doesn't try to explicitly address distortion. They aim to treat the distortion as a learnable function. These are mainly focused on transfer learning. So you can take some off-the-shelf network and transfer it to apply it to spherical images. Ideally, it's adapting to learns to adapt to the distortion. It's often there's like a modular mini network that you can just sub into the beginning of your network that should do this. Oops. The problem with this is that while they are, you know, by definition transferable, that's what they're designed to be. They also scale pretty well because they are not, because they're just a simple module that you add to an existing network. So they'll scale at least as well as that existing network. They don't sufficiently address distortion. As it turns out, the distortion is not sufficiently learned by these approaches. They don't see the performance boost that you get when you directly adapt to distortion. Now, this final group are location adaptive. Sorry?
One moment. Why is that? Is that if we're trying to learn the distortion function, it's not as well? Is there an explanation or?
Yeah, so one of the big reasons it doesn't learn as well is simply because for spherical distortion, at least for equirectangular images and even for cube maps, the distortion effects extend really beyond the receptive field of the network. So oftentimes we talk about receptive field as, well, if we just keep expanding based on how we stack these convolutions, you know, in theory, the receptive field can be much larger than the image itself. But in practice, the actual receptive field is much smaller. And what ends up happening is convolution being local, as you aggregate, you know, the first pass over, you're missing some information. Now, when you're aggregating that, you're actually kind of propagating that error. That missed information is getting propagated through. So you might be able to learn the function, but if you're not sampling all of the, you know, like all of the relevant information from the image in the first place, there's not much you're going to be able to learn. So kind of give a tangible example you might be able to picture. If you can think of a big wall that has a picture in the middle of it, and due to spherical distortion, the wall has been expanded and effectively the picture is contracted, where you may have gotten a lot of picture information before, like, you know, whatever's hanging on the wall may have been sampled by the filter. You might be getting only 1 pixel of that and getting a lot more wall. And from that, there's not much you can do to learn to expand the filter short of actually sampling differently from the image. Does that make sense?
Yeah. Also, another question about this. It's a tough one, maybe. Is there another example where we can see that sometimes trying to learn a function with convolution is not as efficient, which is not a spherical distortion example? Because it's the first time I'm encountering something like this, and it makes me think, where else does it happen?
So I didn't think to put anything like that in my talk. I mean, there typically where at least in my practical understanding, where I've run into this is not always spherical images, but it's anytime there is any sort of real scale deformation. And I do have a slide on this later where just perspective distortion, and I call it distortion, it's not really distortion, but the different cameras, so different intrinsics in the camera can affect how you capture an image. And that will actually also impact performance, but it's not so much efficiency. It's definitely much more like the output performance of the network. So, you know,
the accuracy.
Accuracy, yeah.
Yeah. So interesting. So for example, if I want a task that is estimating camera's parameters, its field of view, its focal length, solving this task is not trivial using neural nets, basically. This is what we can get from here.
Yes. There's actually been some cool work. There's a paper called CamComp, I think. I'm blanking on the first author's name, but it was out of Javier Severa's group. I'll try to send it afterwards, where they actually, for depth estimation, turns out knowing the focal length and things like this for the camera makes a huge difference, even for deep learn depth estimation. And they show a module that can learn the intrinsics in order to improve depth estimation. So it definitely comes up in other areas as well. Yeah.
Jan is asking here. By the way, Jan, feel free to use the audio. He's asking here also something.
Yeah, so I see wraparound and feature. So will I also talk about wraparound feature detection across the X boundary? So not explicitly, but actually it comes up right now. So with the next category here, these location adaptive convolutions, they are designed to explicitly wrap around the X boundary. So they will adapt where the kernel samples where the certain kernel samples from the image in a location dependent way. So if you're sampling right on the boundary, it will actually wrap around by design. And so because of this, they're designed to be a drop-in replacement for 2D convolution. They can handle the wraparound. They're basically the convolution operation. They just adapt the location. These are kind of like an a priori version of deformable convolutions. So deformable convolutions are often learned. You learn the deformation. This is, hey, we know what the deformation is because it's a spherical image, so we're just going to encode that in our convolution. Now, because they are designed to be a drop-in replacement, they are transferable. You can swap in a location adaptive convolution for a standard convolution to any network, and it'll just adapt where it samples. You don't have to change the weights or anything. But it raises the question whether modifying sampling goes far enough to fully address spherical distortion. As it turns out, it doesn't really. It also raises the question of, does it scale? And we'll also talk a little bit about why it doesn't scale as well as we think it should. Before we get into all that, though, let's do a quick recap of spherical distortion. So basically, it's mathematically impossible to remove. And it works by spreading and deforming content in the image. And this disrupts the translational equivariance that is critical to CNN and feature matching and other algorithm functions. And there's some remaining questions that haven't really been answered. One I just mentioned, is modifying the image processing tools enough to restore equivariance? Something like a location-dependent convolution, does that go far enough? What about the content deformation? If we're just changing where we sample, does that fully handle the fact that what we're sampling is deformed? And then our cube maps and equirectangular images really are only options. So unlike traditional lens distortion, as I said, it's a consequence of physical properties of the camera lens. Spherical distortion is a function of our choice of representation. So maybe there's a better representation than what we're using. And this kind of brought this question to mind to me. When I first started thinking about all this, I realized that, well, maybe this is new for computer vision, but cartographers have been trying to address this problem for over 2,000 years. It goes back to ancient Greece with different map projections. So surely they must have some useful insight. Sure enough, they do. So as I discovered, the 20-sided regular icosahedron is considered among the least distorted spherical representations. In cartography, what they call geodesic grid projections. It's actually used for many applications, including weather and climate simulations. It also has the additional benefit that it can be subdivided, meaning each face can be broken into 4 equally sized smaller faces. And this allows us to get increasingly close approximations to the sphere. And if we were to unfold that original 20-face icosahedron and we were to superimpose Tussauds and Decouples on it, you'll see that there really is very little distortion. Remember, we want perfect circles. That's what we want on our planar representation. And here you can see this is much better than the equirectangular image and cube map that I showed before. But we now have a problem, which is that convolution and many of our other algorithms is designed for a pixel grid. The icosahedron is tessellated by triangles, meaning it's broken up by triangles instead of squares. So how can we convolve on this? Now enter researchers. So despite this representational drawback, the icosahedron has gained popularity among a lot of recent work on this topic. 5 separate papers touting its benefits were published in 2019, And each one proposed a different way to handle the representation issues. So, you know, we were talking about those 3 different classes. This is kind of a 4th class of how to address this. And this really showed up in the last, at this point, it's been about 18 months. Now, all of these works are built around this useful analogy between subdivision and image image upsampling and downsampling. So if you look at the bottom, we have a pixel grid, and above it, you see a regular icosahedron. When we upsample the image, each of those pixels become 4 pixels. Similarly, if we were to subdivide an icosahedron, each face becomes 4 faces. Now, here are the equations on the left for the number of faces and vertices. Don't worry too much about the numbers. Thing to note is this factor of 4. So this is really nice because our convolutional neural network paradigm, at least, is heavily built on this idea of encoding through downsampling and decoding through upsampling. So this factor of 4 paradigm is kind of naturally built into how we think about convolutional neural networks. So it's nice that this icosahedron parallels that. This simple analogy also allows us to associate icosahedral representations with an equivalent equirectangular representation. So we can see here is like on the top, so like level 0 is the basic icosahedron, level 1 has been subdivided once, level 5 is subdivided 5 times. And you can see how it associates with an equirectangular representation at the bottom. But notice that this recent work, they've all focused on level 5, 7, and 8. But I want to draw your attention to these numbers I'm highlighting in green right now. These are the angular resolution per pixel in the image. So this is the number of degrees that our field of view that gets discretized into a single pixel. Now, if we compare this to a standard VGA resolution central perspective image, this VGA image has an angular resolution of
We lost him right on the interesting part. Yeah, here. He'll be back soon. So Jan Schmidt, right? Jan is the name, am I correct? You wrote you're working on Linux drivers for VR headsets. This is very interesting. I have friends here in Israel working for Magic Leap, developing the on-chip platform there. There's a lot of stuff there. Are you doing this by yourself, or is it part of a company? Very quiet. I think maybe he's typing, not sure. Maybe he can't use the audio. Let's see who else wrote here about his Singapore, working on human poses, Stanford. I think somebody last week on the HRNet lecture was also working on human poses for healthcare. I'm not sure if it was you or somebody else though. What else do we have here? Who else wrote something? Ah, okay, cool, cool. Were you, by the way, the one who also asked on Discord about research for medical imaging? Not sure, I don't think so. No.
Should we post little bios so we can?
Yeah, please. I'm fascinated to hear what everybody's doing for sure.
I think we've got Mark back.
Yeah, sorry about that. It's actually Zoom that's crashing for me, not. Yeah, anyway. But,
yeah, somebody wrote here that Zoom are experiencing like hacker attacks. So maybe that's the reason.
That's never what you want.
Yeah.
Yeah. Okay. Can you see my screen again?
Yes, we can.
Yep.
Cool. Yeah. Sorry about that, everybody. Yeah. Basically, so did you hear anything on this slide?
Yeah, you just got to the 480 by 640 pixels, the
Cool.
VGA image.
Awesome. Yeah. So basically, yeah, the VGA image has an angular resolution of 0.094 degrees per pixel, which means this is significantly lower than the highest spherical image resolution that these other works have processed. But so this gets back to that issue of scalability that I mentioned early on. If we discretize the world into pixels, we're inherently performing a lossy operation. For spherical images to capture the world with the same level of detail as a central perspective image, it's got to have a much higher pixel resolution because it's got a much higher, it's got a much wider field of view. Otherwise, we're going to miss out on information. So now this VGA resolution image is actually most comparable to a level 10 icosahedron or a 4K equirectangular image. And the problem that we have is that these methods are generally unable to scale efficiently to that resolution. Now, the logical question is why? Well, the simple answer is because they all modify the convolution operation. Because they're all built around the icosahedron, each of these methods does sufficiently address the spherical distortion problem. But most of them don't scale. The one that does scale somewhat efficiently, it's actually a type of reparametrization method, which if you recall, this isn't going to transfer. So 3 of the other methods do propose a way to transfer traditional networks, but they're held back by their inability to scale as efficiently as networks for central perspective images. One of the big reasons for this is because by changing the convolution operation, they can't take advantage of the efficient convolution implementations and their associated hardware optimization. So like NVIDIA's cuDNN library. Additionally, they're all built around this notion of additional subdivision to represent high resolution images. And this starts to compound as we need increasingly more mesh elements to handle these high resolution representations. And it takes up quite a bit of memory, and it actually leads to poor data locality in memory when sampling. And so this also has a tendency to slow down our convolution operations. But so given this issue, one interesting thing to observe is that when we use a subdivided icosahedron, distortion is more or less mitigated by the 3rd level of subdivision. So this plot on the right shows a metric. It's the ratio of the surface area of the subdivided icosahedron to that of a sphere. As the ratio approaches 1, we approach a perfect approximation. But so now look at that red line at level 3. This is where we start to see diminishing returns in terms of distortion reduction. But because we built on this analogy of image resolution and subdivision level, current methods have to continue to subdivide. And as I mentioned, this is one of our sources of our scalability issue. It's also worth noting that the best performing work out of those 2019 papers uses the unfolded representation. It's called like the net of the icosahedron. And this has distortion characteristics equivalent to the simple 20-face not subdivided icosahedron. So it seems that maybe for certain tasks at least, distortion can be sufficiently mitigated without the need for excessive subdivisions. So these observations raise a few new questions. First, can we find a way to leverage both the icosahedron and the standard 2D convolution so we don't have to change the convolution operation? That will give us both scalability, at least scale as well as existing algorithms, and transferability because we won't have to change it. While using the icosahedron will reduce distortion. Additionally, can we find a solution that allows us to modulate our distortion depending on the application? Certain applications might be capable of handling higher levels of distortion than others. Remember how I was talking about, localization doesn't get affected by distortion quite nearly as much as a dense prediction task would. So if we want to provide this tunability, we're going to have to untether our input spherical resolution from our subdivision level. Now, as an answer to these new questions, we'll get to kind of my CVPR paper. I proposed this new representation called the tangent image representation at CVPR this year. Tangent images are the mnemonic projection of a spherical image onto square, oriented pixels set tangent to the sphere at the center of each icosahedral face. Now, that's a mouthful and there's a lot packed into it, so we can break it down a bit.
I was gonna say that 5 times quickly.
Yeah. So first, let's say a mnemonic projection. It's simply the projection of a sphere onto a tangent plane. This is actually our perspective projection that we're very familiar with for most cameras. Now for tangent images, we determine the placement of these tangent planes according to each face of a subdivided icosahedron. Now a key concept is that these tangent planes are all going to be oriented according to a fixed coordinate system. So this allows us to associate with the orientation of a spherical image. And this fixed coordinate system is, we choose that based on the orientation of our image. So now we have a collection of square planes. We can tessellate these square planes with squares and turn them into pixel grids. So then to create tangent images, we just render, these pixel grids. In this figure, I'm just showing a select few of the tangent images. And here you can see kind of a clipped visualization of the complete tangent image representation with the wireframe of the icosahedron that we used kind of stuck in the middle. And here you can see it in action. So they're rotating. This is representing the sphere. Okay, so I'm going to talk for a minute about how we generate tangent images. I'll go into some detail on this just for the sake of understanding the nomenclature when I describe things later. But basically, the first step is we set a base level of icosahedron subdivision. So we call that B. For example, if we set B equals 1, we're going to derive our tangent images from the faces of a level 1 subdivided icosahedron. Now, when we set this base level, we determine 3 things. First, the number of tangent images, which is going to be equal to the number of faces at this base level. Second, the distortion characteristic of the tangent image. You can look at a base level 1 right here. Notice a low distortion characteristic as shown by these Tissot's indicatrices that I've superimposed. For perspective, you can see the associated icosahedral face is projected on the image in yellow. So you can see how the tangent image overlaps the face. So these actually have natural padding built in. Then the final attribute is that the base level determines the field of view of the tangent image. A base level 1 results in a 51-degree field of view. And these are all square images. But I want to pause real quick and I want to highlight a useful observation here. I didn't choose base level equals 1 arbitrarily. Turns out that this is really the best base level for most of the applications we experiment on. And if you think about why that might be, recall that tangent images are formed via the mnemonic or perspective projection. This is synonymous also to rectilinear projections that we use to form central perspective images. Now, if you've ever dabbled in photography, you may recall that the standard field of view for a rectilinear prime, like a rectilinear prime lens, it's going to fall about 25 to 60 degrees, depending on the lens. So basically, here we have an image formed via the same projection and the same field of view range as a central perspective image. Effectively, what we're doing is we are using a principled way to resample our spherical image into a collection of central perspective images. And this is what's going to make a big impact on our ability to transfer networks to spherical images. So now that we have set a base level, we need to now determine the pixel resolution of our tangent images. So let's say we have a spherical image with a resolution S, where this is in terms of the equivalent icosahedral subdivision level. We can set S equals to 8 maybe. We can then compute the dimension of our tangent image D by this relation of D equals 2 to the S minus B. So basically for level 8 input with a base level 1 icosahedron, we get 2 to the 8 minus 1 or a 128 by 128 pixel image. And I want you to just notice this relationship again, because just like image upsampling and downsampling, and just like subdivision, with this relationship, we're able to scale up and down by a factor of 4 each time. So this 2 to the S minus B is each dimension of our tangent image. So, you know, it's this squared, which gives us 4, right, to the S minus B. So this is nice. It allows us to keep that existing, factor of 4 paradigm that we like so much. And here you can see an example of a set of tangent images. This is the original image on the left, taken from a public data set, Stanford 2D, 3D. And on the right, you can see the 20 tangent images we generate at a base level of 0. So I want to highlight again 2 important properties of this. First, we're deriving from the icosahedron. So we're taking advantage of those low distortion benefits. But we have an oriented pixel grid representation, which means that we can treat this like any other image. And because the distortion is low, we should be able to take off-the-shelf algorithms and have them work quite well. So it means that we're going to have minimal distortion and we don't need any fancy tools to apply our off-the-shelf algorithms. In fact, in order to use them, all we do is take our spherical input, render it to a set of tangent, apply our desired algorithm on these tangent images, and then take our outputs and render them back to our spherical representation. And I want to reiterate this again, just because it's one of the exciting things about tangent images. All you need to do is apply 2 resampling operations, one to create and one to transform back. That's it. Once you have tangent images, apply whatever computer vision algorithm you want. So I'll go through some of the experiments we ran. I'll refer you to the paper because I know we're coming a little long on time here. But we'll mainly focus on some of the qualitative results. But let's look at how they perform. The first thing we did was we applied semantic segmentation. We wanted to, our goal here was really wanted to hit high resolution semantic segmentation. So processing level 10, icosahedral resolution, which is like a 4K equirectangular image. So this is kind of similar to that VGA central perspective image. The way we work with tangent images, we pass all, during training, we pass all of them through, make predictions on all of them, and we back propagate the error for the entire set of tangent images at once. So this way we can effectively account for the fact that we're breaking up our field of view because we are still back propagating the error from the full field of view in one fell swoop. So we use 2 standard metrics. It's mean IOU and mean accuracy. And I had a way I put this together, a little teaser here, say, hey, wait a second. How come tangent images don't do as well as that best performing paper from 2019? Well, it's because if you look at the input resolution here, they're using a level 5 spherical image. So here's an actual size level 5 spherical image for reference. Now, these have an angular resolution like that of a 16 by 16 perspective image with a 45-degree field of view. So this is like half of a thumbnail image. Now, tangent images take this already low angular resolution image and break it into low pixel resolution images. So in other words, at a low angular resolution, at a low spherical resolution, tangent images are taking images that have very little content and breaking them up into smaller images with less content. But look at what happens when we instead evaluate on high resolution spherical data. We get a 10.5% improvement in accuracy and an 8.5% improvement in IOU over the top level 5 results. But remember, no other method can operate at this level. By our resampling algorithm, we are able to extend to much, much higher spherical resolutions than prior work. So for perspective, here are the actual size of the image we train on. So this is your 4K equirectangular image. And this is an example of a 512 by 512 tangent image at base level 1. So unlike at level 5, we can clearly see that the occupant of this office has the misfortune to be a New York Jets fan. It's American football. I'm a big New York Giants fan. They're
oh my goodness, I love it.
Yeah. So here you can really see the difference, right? So this is actual relative image size between what we operate on with tangent images on the left versus the prior work on the right. So it's a much higher angular resolution image. It's much more similar to what our standard networks will use as central perspective image, right? Most of our networks take a 480 by 480 image like it's no big deal. And here's some qualitative outputs. Let's take a look at these images here. I want to particularly, we got the input and the ground truth on the top, and we've got different levels of prediction at the bottom. And I want to draw your attention to the chairs. So if you look at level 10, the granularity and accuracy of our segmentation is much better than when we look at level 7, which is much more pixelated, and level 5, where it's not really even clear what those blobs represent. So these results are indicative of the accuracy benefits we get when we can process high resolution spherical images scale, because we can end up getting much more granular segmentation. So we also looked at network transfer, because remember we talked about transferability as one of the key kind of tenets that we need to achieve. For this, we trained a network on central perspective data, and then we evaluated it on spherical data. So there was no spherical data in the training process. The idea here is we want to be able to see our network preserve the performance between the representations. So basically, let's say if we take an off-the-shelf network that has 60% accuracy on central perspective images, and then apply it to spherical images, we wanted to get at least 60% accuracy on the spherical data as well. In theory, however, the extra field of view of a spherical image should provide additional content and context for the network. So ideally, we should actually see improved performance when we apply our network to spherical images. So we use the same accuracy and IOU metrics, but I also add what I call the percent network performance preserved. So I should have done a plus or minus percentage, but instead I did it out of 100%. So if percentage is equivalent on both perspective and spherical data, we would say that we have 100% performance preserved. But if the transfer performance is better, then this number is going to be above 100. So here are our results. Right off the bat, simply using tangent images, we were able to preserve about 96% of network performance. What this means is that take any off-the-shelf network, for in this case semantic segmentation, and apply it to a spherical image, you should see about 96% accuracy compared to what you had before. Now, prior work hasn't really done this experiment on this data set, but one does provide quantitative results that we can look at. And it looks on the surface like they do very similar. This is that Zhang et al. Paper. About 96% of accuracy is preserved. But notice this FT10. What this means, this is that these results are after 10 epochs of fine tuning. So we take something off the shelf and get 96%. This prior work had fine tuned and it was able to get 96%. So this kind of begs the question, what happened if we fine tune? Well, after just one epoch of fine tuning on spherical data, we find that we basically get parity in our performance. We preserve roughly 100% of our accuracy. But if we were to fine tune for 10 epochs like this prior work, we actually start seeing that wide field of view start helping us. We end up getting better performance. That's why it says 104%, because it is 4% better than the perspective image performance. And we do fine tune on the perspective data as well, just to normalize, so it's an apples to apples comparison. But this is huge because it means that we've mitigated distortion enough so we can start tapping into those hypothesized wide field of view benefits.
A quick question about it. How were you able to get the matching of perspective and spherical images? Maybe I missed something on the way there. So
So this is kind of a nice quirk of the data set we used. So this Stanford 2D, 3D data set is a public a selection of perspective images from scenes captured with a Matterport camera. Mm-hmm. They also have the 360 equirectangular images for all the same scenes. So the content is the same in both. The only difference is the capture format.
Yeah. Okay. Cool.
Yeah. But so that way we're able to keep kind of the scene as controlled as possible. Now, yeah. Yep. Okay. So cool. One interesting outcome, and this is something I was mentioning earlier about like a broader takeaway. One interesting outcome of this transfer experiment is that it kind of motivates an important idea that applies more broadly than just to spherical images. So if you look at these three images rendered from the same scene, this is a synthetic data set, but I just render it at different focal lengths, you can see that depending on how we change these values, an image can look quite different. So anyone who's played around with the camera knows this, right? Each image is going to be the same size. When you change the focal length, give a specific field of view, objects in the image could appear larger or smaller as a result. This is how zoom works. Not this zoom, but zoom on a camera. Now, convolutional filters are going to learn to associate labels with patterns at certain scales. So effectively, these filters are learning to fit a certain angular resolution or range thereof. And if we deviate from this too much, it's effectively scale distortion, which is going to impact this, our performance. So in our case, when we performed our network transfer, we performed a camera normalization step on all the perspective image inputs, and we did this as a pre-processing. So we resampled perspective images to all have the same angular resolution, that is the same camera intrinsics. And we chose those intrinsics based on the spherical data, based on the angular resolution of the spherical data we intended to test on. And so we did an ablation study here, and you can see the importance of this step. So this is, we trained using the angular resolution of a level 8 icosahedron. Then we evaluated it at different spherical resolution levels. And you can see that performance drops off considerably as a network gets evaluated on images that have a more dissimilar angular resolution per pixel. Now, this result suggests a few things too, right? Because first, camera intrinsic information is clearly not irrelevant for deep learning. Oh, excuse me. There are a few recent papers that have demonstrated this for depth estimation. I mentioned that CamCom's paper, which I'll include in the kind of resources that I'll share after this. Second, the second thing here is also if you know the camera intrinsics and that you plan to use at inference time, it can help to normalize your training data to the same camera. So this is kind of useful for any sort of embedded camera where, let's say you're building a device that's going to use a specific camera. It doesn't have like auto white balancing or anything like that, or autofocal adjustments the way like your iPhone might, but you know what the intrinsics are going to be and they're going to be very close to fixed. It means that you can actually train a network to be specialized to that camera. So this is kind of a cool outcome. And then the third thing is that this might suggest that random camera matrix resampling may be a useful augmentation strategy during training. So just resample randomly to different intrinsics in order to make your network more robust to scale. But anyway, I thought this was a pretty cool result because it demonstrates that angular resolution is important when thinking about deep learning models. In a way, it's almost like there's a real relationship between the configuration of the 3D world and how we can evolve on the 2D image. This result might be something worth keeping in mind even beyond 360 vision. So I'll have a couple more qualitative examples and then we'll wrap up. But if you recall that spherical I talked about, it was not just deep learning. Spherical distortion affects sparse feature key points as well. And so we looked into this in the tangent image paper, and we found that tangent images provide a significant boost for the sparse correspondence matching performance in the same way that it improves deep learning or convolutional neural network performance. So here's a qualitative example. If we compute SIFT key points on an equirectangular image, we end up with what you see on the bottom here. Spurious points in these distorted regions like the floor and the ceiling. And this noise impacts our downstream tasks. It makes it harder or slower to properly find image correspondences. Now, if we detect on tangent images instead of equirectangular images, we get many fewer noisy points, and we found that this creates a sizable improvement in the subsequent correspondence matching problem. There's a way to quantitatively analyze this, and I'll refer you to the paper on that. But if you can see how a tangent cleanly detected on the floor and the ceiling, adhering to lines.
We can't hear you. I think, again, his Zoom has crashed. Gone again. Yes, you were quick. Oh, no. There we go. Happy to talk about it for like. So, in the meantime, I have a question for Mark, but I will also ask the audience. There are some people here who are familiar with these things, which is good. Photogrammetry today is turning a lot to deep learning. And I was asked the question, why? Why not use the old school methods and improve on them? Why do people focus so much on deep learning and not on the old school math? So one reason, of course, is the trend. Everybody is interested in deep learning because everybody's interested in deep learning. But is there another reason? Did anybody check into it and can say something about it? I had an explanation, but I want somebody else to say first, and then I'll say mine just to, So to not get you biased on my ideas.
Well,
Okay.
oh,
Sorry.
right.
We good?
Yeah, I'm like your filler guy. Whenever you're out, I'm trying to, you know, fill the spot in the meantime with trivia.
I
Yeah,
appreciate it.
really
I'm
good.
sorry for the trouble, everybody. We're wrapping up, so don't worry. Hopefully that'll be the last crash. But yeah, anywho, I'll keep going. Basically, I was trying to say that you can see the qualitative difference here. Basically, and in terms of quantitative measures, we get a 4 to 5% improvement in the quantitative metrics for key point descriptors as well. So this just reiterates widespread benefits of tangent images. By using a low distortion spherical representation in the form of a standard pixel grid, we're able to impact 360 computer vision beyond just deep learning. Now, the last brief experiment I just want to show, this isn't in the paper, but I thought it was pretty cool that it goes beyond just key point detection. Even low-level vision tasks as well are improved if we can reduce distortion. So if we use equirectangular image and we run the common canny edge detection algorithm, we get a lot of spurious edges. Like look at the floor in particular. You see all those, like that's all noise. We don't want that. So the traditional way to filter out these noisy edges is we increase the sigma parameter, so that the bandwidth of our smoothing filter in this edge detection algorithm. But if we increase it, we get rid of the distortion-induced noise, but it comes at a cost of detail, like the edges on the ceiling, and we get lower edge strength. So you can see the brightness of the edges is a little lower. If instead we use tangent images, we can get the same high frequency detail that we had in that first output, but without the distortion-induced noise effects. So this is just kind of another pretty cool experiment, qualitative result. Anyway, we're about to wrap up. So before we do, let's look at some of the takeaways from tangent images. So these are the big takeaways from my CVPR paper. If we look at our 3 guidelines again, tangent images built around the distortion, built around the icosahedron. So we address distortion pretty well. They scale at least as well as your existing algorithms because they're designed to use a standard pixel grid like anything else without changing any of the algorithm operation itself. And they transfer quite well for the same reason. Now, the big reason that tangent images achieve both scalability and transferability is because we design them around current optimizations. 2D convolution is so ubiquitous that it's being physically embedded in chips. Why fight progress? Instead, let's try to find a way to make it work for the problem we want to solve. Another cool takeaway is that once we get the distortion out of the way, we can actually tap into improved performance of the ultra-wide field of view that 360 provides, which means that we can do more with 360. And then finally, tangent images, this is maybe a little pitch of my own work, I think they're a promising general solution to this spherical image problem. And they are the first contribution in this area of the field that can be leveraged for both new advances in deep learning as well as improvements in traditional vision problems as well. So I hope you take a few big picture ideas away from my talk today. First, that there are many opportunities for 360 vision, immersive virtual experiences, particularly now as everything's becoming remote, medical imaging, robotics, autonomous driving, basically anything that you could think of that might want to use eyes in the back of its head, benefit from 360. But if we want to enable these applications, spherical distortion must first be addressed. Otherwise, it will destroy the translational equivariance that is required for the proper functionality of CNNs, as well as many of our other vision algorithms. And because spherical distortion is a function of our choice of representation, the image representation matters a lot. One thing to remember is that a good choice of the subdivided icosahedron, a good choice of representation uses the subdivided icosahedron or some derivation thereof because of its nice low distortion properties. Now, lastly, if we want to truly unlock the potential of 360 vision, 2 elements that are paramount are scalability and transferability. The key to efficiency for convolutional neural networks is to minimize modifying the kernel. We want to be able to keep using cuDNN or other sorts of hardware optimized implementations of 2D convolution. So I suggest that instead tangent images provide this scalable and transferable approach And they're a promising method that will satisfy all of our 3 necessary properties of a general solution to the problem. So in closing, I want to leave you with a few final thoughts. First, 360 is exciting. There's lots of exciting applications so long as the tools are there to enable it. So I encourage you to think about this problem more and potentially try your hand at improving on this even further. But remember that it's not enough to simply solve the distortion problem. It needs to be useful. For that, scalability and transferability are necessary attributes that should be kept in mind when you come up with any solution. And finally, I will say again that I firmly believe any general solution is going to be found by focusing on the image representation rather than the processing tools themselves. Why change a million things when you can just change one? So with that in mind, I hope that the tangent images can become a step in the right direction here. And I encourage you to continue building on this work. Here are some citations from just the figures I used. I'll send out a full citation list, a good reading list. And here are QR codes. On the left is that Medium post that I wrote that kind of gives a lot of this information. And the right is the archived version of the tangent images paper that I talked about in the second half here. And with that, are there any questions?
I have, but I think probably others have first. Mark,
Okay.
if you could put the previous slide before so that we have it in the background with the QR codes.
Sure.
Yeah.
Maybe not. Oh no, am I freezing again? Now PowerPoint is crashing. Okay. All right.
No worries. It's okay. It's fine.
I'm going to put those QR codes back up, but it might take a second.
That's fine.
Okay.
I just hope you're still here with us. Yeah, you are.
I am, yeah.
So Ina is asking a question
today.
Yeah, it was a bit, but it's okay. We had nice chats while you were reconnecting. So Ina has asked, are there data sets recorded with such cameras recorded? So first, I can also answer this. Yeah, there are data sets with 360 cameras. The Matterport data set is a good example. I personally tried working with them a bit actually, but Mark, maybe you know of other data sets to recommend. I hope you're still here. Your screen seems to be stuck. I think Mark has left the Zoom again. So Ina, yes, we will send in the references to this talk, the data set, so you will have it. The URL in the chat, I will put it in Reddit. It'll be there today, so you could get it. That URL and many others. Just I need to bulk it in one go. Mark, are you back with us?
I am. Yeah, and here are those QR codes. I'm not even going to try to start the presentation because, yeah, these are the QR codes here.
There we go.
Yeah, sorry about that. The question was about data sets.
Yes, so Ina asked, are there data sets recorded with such cameras recorded? Are there data sets with 360 cameras?
Yeah, oh yeah, there's a bunch. Matterport, I heard you mention. There's also the Stanford 2D, 3D. There are a couple synthetic data sets. Some like from the Cynthia data set, for example, basically they take the Cynthia cameras and they stitch them together to create it's Omni Cynthia is the name of that data set.
By the way, everybody, I sent on our Discord a list of about 50 data sets of this character last week. You have it in the reference, I think in the announcement section. It's a spreadsheet I built. Yeah. Mark, you might actually also like the community there. We talk exactly about these things. How do they install this? So Ina is asking, what about these cameras install? How do you install these sensors? They are not very friendly by design. I think again, we lost him. Again. I am actually, me personally, I'm not sure I'm understanding the question. What do you mean install these sensors and that they're not friendly?
Okay, I'm back, by the way. I'm just going to not try to share my screen. I think that's what's killing me.
That's okay.
Automotive require sensors to be very small. Yep, so, I mean, oftentimes what you get with in generating these spherical images, these 360 images, you can do it via stitching. You can have a camera rig that has an effective center of projection. So basically, you design the setup so that they also you have a bunch of cameras that share the same center of projection. There's a company called Circle Optics that's creating a camera like this. Now, there's also just fisheye cameras suffer from the same problem, and those are often installed in automotive applications, in cars and robots, but they have the same spherical distortion problem. Although we talked about the full 360 by 180, a fisheye, you might get a 180 by 180 or a 2 by steradian field of view. But in practice, what ends up, yeah. Cool, thank you, Jan. I didn't know that. That's how BMW works. I know there's, who's it, Volvo has the disappearing trailer that they use. It's like if you have a trailer on the back of your car. Ah. Yeah,
So,
okay,
so
cool.
Jan, I'm actually going to read it out for everybody watching it on YouTube. Jan mentioned here that BMW do it with 4 fisheye cameras, front, rear, wing, mirrors, and stitch the 360 view. That's very interesting. Thank you.
I used to work for Continental, who make these cameras for people like BMW. So I've got, if you have questions which are specific to automotive, I'm happy to answer.
By the way, William, you feel free to also join the answering here if you have.
Yeah.
input.
Yeah. I mean, like I say, with automotive, the cameras are quite small. They're fairly cheap to manufacture. The volume in which they're made is astounding. The company I was working for was kind of gearing up to make 1 million of these panoramic cameras a day by the mid-2020s. So that's just, huge manufacturing volume. And yeah, the number of video streams per car, you can have 4 surround view cameras, but it's not unusual to have 6 to 8 video streams on a vehicle. So the amount of data is quite significant. The cameras, go on.
Sorry, out of curiosity, when you say these panoramic cameras, were they fisheye or were they full 360?
So each individual camera has about 180, just slightly more than 180 degree field of view. They're sort of 1 or 2 megapixels, probably a little bit more by now. Yeah, so typically they're placed 1 under the badge at the front, 2 under each wing mirror, and 1 just above the license plate at the back. But obviously it varies. A lot of it's sort of to fit in with the styling of the particular vehicle.
Gotcha.
And you can do a whole bunch. So you're talking about, projecting onto tangent images. It depends on the company. Different companies have different approaches, but a lot of people kind of reproject into different spaces for particular applications.
Yeah.
Obviously, big. Go on.
Oh no, I just know I was speaking with some folks. That workshop I organized at CVPR, I was co-organized with some folks from Valio, and they're a large. You're familiar with Valio, yeah? They're
Yeah. In Galloway, right? Yeah,
exactly. They're a large. For those who aren't familiar, they're apparently a very, very large French company, one of the larger manufacturers of smart vehicle automotive parts, and they have a lot of computer vision researchers. But one of them was telling me that they don't like these reprojection or resampling algorithms for vehicles because it adds overhead, like time overhead, and when you're something moving at 60 miles an hour, milliseconds are at a premium.
Also, if you're making 1 million cameras a day, every euro cent you can knock off the price of your bill of materials matters a lot. So there's a huge emphasis on putting these onto the smallest and cheapest socks, smallest and cheapest hardware that you possibly can. So, not everyone has an NVIDIA Tegra to run these things on.
That's interesting. Really interesting. Thank you.
So a lot of these things are not necessarily based on deep learning. Yeah, it's not necessarily because deep learning doesn't work. It's because it's expensive.
And this leads me to the question I asked. I think some of you answered. Mark, I would love to hear also your input. I got asked this question before. Today's research with 3D reconstruction, with 360, with keypoint matching, everything to do with understanding the depth and the environment around us from an image is focused on deep learning. Or at least it feels this way for us, because we're coming from deep learning. Maybe it's not true, but the feeling is that it is true, at least the research part. First of all, do you agree with it or not? And if yeah, why do you think that is?
Well, I mean, I'm happy to share my opinion, which is, so my advisor, I'll say I'm biased. My PhD advisor, his whole, like, if people know who he is, it's because of his contributions to large scale structure for motion, which is like very traditional computer vision. He's not a deep learning guy. And so perhaps it's his influence, but I'm of the opinion that deep learning is, it's the present, it's probably the future, but deep learning without geometry is kind of a fool's errand. And we're starting to see, I mean, you see more and more approaches that are leveraging geometry, they're leveraging graphics, a lot of neural rendering. That's a topic you might want to cover in some of these. Maybe contact the authors of that NERF paper. It was ECCV, it was a very good paper.
I'm going to ask you after this call to get to, if you can, to give some introductions, because it's hard for me to contact authors out of the blue. If it's possible to get an intro, it's the easiest way. I would love to.
I can try. I definitely try. But yeah, to answer the question, I think it's, I mean, deep learning is a great solution, but without geometry, I mean, we're just looking at pictures and guessing. When there's actual geometry, it also allows us to have explainable results, right? Hey, how come we have the classic example of deep learning applied to like traditional vision algorithms where the outputs are kind of, you got to raise your eyebrows a little bit, is PoseNet. That was a paper from like 2015. And they basically just took images and regressed the camera pose. And it worked quite well. Then the author's actually a very, very bright guy, big in autonomous vehicles. His name's Alex Kendall. He's got a company called Wave, I think it is, or in the UK. But he then published this post, and his follow-up paper is basically like, hey, PoseNet worked, but it shouldn't have worked, and we shouldn't look, it's naive, and we need to do more with geometry. And it's come a long way since then, but I think, that's my point of view. I think deep learning with geometry, and we can do some pretty cool stuff, but deep learning without geometry, and we're just looking at pixels and making guesses.
By the way, I'm currently building a project plan for exactly something in this sphere. And that's exactly what we're trying to tackle. How can we fuse deep learning with geometry?
I think you do need to go one step beyond that, though.
Okay.
So my recent background is my interest is in safety of machine. So my interest is in machine vision systems for vehicles. I used to run the test group for Continental Surround View, testing the algorithms. So my background is very much in sort of both as an algorithms engineer and also as a person who's kind of responsible for quality and testing. So I'm very interested in trying to push forwards to a point where we can use these techniques in a safe way. What I'm interested in is, so recently I've had a couple of roles in companies using synthetic data to train the neural networks. So we're looking at vision as essentially an invertible function. We know the forward function from graphics. We've got software which does that quite efficiently, and then we can train our neural network to invert that function. But then we want to take that capability and tie it back to requirements. Because one of the problems when we are training a neural network with recorded data is we have very little control. This used to be my job, to manage the team, to go out and record lots and lots of data in the real world. And it turns out it's actually really, really difficult to control the environment in which the data is recorded. So you end up with a distribution of data that you don't fully understand and that doesn't match the distribution of the data that your system is going to be expected to deal with in the real world. Now, academically, everyone says, okay, you need to match your training data distribution to your operational distribution. Actually, I dispute that. I think that in a real, engineering environment, what you want to do is understand your training data distribution. And that's actually much more important than it matching. So this comes back to explainability and explainable AI is, if we've got one of the things that we need, I believe, is to understand the distribution of the data that we have that we're using to train the neural network. And that's where I think synthetic data is important and has an important role to play. But I also want to think about how we have traceability between our requirements, so we can develop requirements which talk about physical properties of the world. The target aspect, occlusions, lighting levels, atmospheric conditions. So we've got, you know, all of this understanding of what the physical properties of the world are, and be able to draw box distributions over those, and basically understand what the distribution of the training data is, and through that understand what the performance of the neural network is. Because we've done some very simple experiments. We've generated, you know, a sort of 2π steradian view of a car, and generate imagery from all sorts of different distances and you know, target aspect angles. And there is variability. If you take an off-the-shelf neural network, there are certain angles where the performance drops, where the, you know, confidence in the target classification drops dramatically. And that's because those target aspects are undersampled in the training data purely by accident, purely because of the kind of geometric situations which occur in the world. So in order to actually understand the performance, you need to like get away from just relying on real world data and move towards you know, having a more controlled training data generation. And that then also comes into the algorithms themselves, and also making those algorithms more aware of what's actually going on. And so yes, absolutely, geometry, tying things down to the real world is really important. Mm-hmm. And sure, using machine learning, but in a very controlled way. Sorry, that's
Well, one of the things you said about like the distributions, basically trying to, often we seek to match our training distribution to the distribution of whatever we're going to test on. That's actually one of the things that becomes problematic with spherical data, and it's perhaps why when you talk about these 2π steradian images causing problems, it's depending on where the center is of your view vector, you're going to have different levels of pixel redundancy, which affects the input distribution of your training data. And so,
and controlling that is very difficult. Now, actually, when I was talking about 2π steradians, I was talking about, you know, a simple kind of pinhole model taken sampled across a 2π steradian of, you know, target aspect.
Got it.
Rather than a 2π steradian image itself. But yes, you're absolutely right, because, you know, you can set up a real world kind of training data with a panoramic camera, and you move the camera slightly and it's completely different pixel data, and your translation invariance of, you know, CNN just doesn't work. And, you know, well, that's your whole lecture, and you're absolutely right. Everything you said is true.
Yeah.
I don't think we have much time. I do have a question I like asking Mark researchers, and then if we have more time, of course, I would love to, but if not, we can sum up. When you were doing your research, what were the unexpectedly hard things that came by, or things that didn't work as expected, or surprises? And on the opposite, what were the unexpectedly positive things, or, you know, good surprises that you saw happen?
Yeah. So the unexpectedly difficult stuff, actually, before this tangent image project, I was one of apparently five groups of people who in 2019 all independently had this idea of let's use the icosahedron. And so I had read some of these deformable convolution papers. I was like, hey, let's create something where we can just specify how we're going to deform the convolution a priori. We can, you know, this actually be used if we want to adapt a convolutional kernel to depth. You know, let's say we want to have a model, a plane per pixel. You know, hey, this is a really good idea. I went and implemented it, and I was really shocked at the sort of slowdown that you get when you try to modify the CUDA kernel. Oh, no, excuse me, the convolutional kernel and the CUDA library in which this is implemented. Specifically, I work with CUDA because I'm dealing with NVIDIA GPUs, but hardware optimizations, to me, what was surprising is how significant the impact of hardware optimizations are to the growth of deep learning recently, and, you know, the speed that we were able to train our models and evaluate our models. Once you start futzing around with that, unless you really are an expert, which I can't claim to be, I can poke around in CUDA and make stuff work, but it's nowhere near as, you know, it's probably 100 times slower than what the engineers at NVIDIA are doing. But I was really surprised at how much hardware optimizations make a difference, because we often think about software. We often think about what framework we can use, and, you know, how can we make this loop algorithmic improvements, right? But at the end of the day, deep learning is hardware driven, and we just abstract that away. So that was a big surprise for me. Some of the easier stuff was I was actually surprised by how well like just tangent images worked, to be honest. I had this idea and I was trying to, make it, I was thinking, how can I make triangles square? That was basically like, what can I do to make the triangle square so we can just use normal things? Yeah, I was surprised by how much, how easy it was once I had implemented it. But I was also, I was surprised by how little, I guess is another surprise thing, how much of this is actually like drawn from other fields. What I pulled here is like, the whole idea came from PTEX, which comes from graphics. If anybody here is familiar with graphics rendering pipelines and things like this, about 10 years ago, Pixar created this new way of representing high resolution 3D like meshes, textured 3D meshes, by with this method called PTEX. So previously, if you wanted a high resolution animation, let's say it's I don't know, let's say it's Woody from Toy Story, and you wanted to make it high resolution, you would add more mesh elements. You'd have more faces, more vertices. But what I guess they discovered is you can actually fudge a lot of that with texture. So like good texture can give you the same effect, but if you want high resolution texture, you don't need high resolution meshes. You can just vary the resolution of the texture for your quad independently from the actual resolution of your mesh. And so what they did was they started using quads exclusively, so no more triangles. And each quad had, instead of mip-mapping, each quad had a designated texture. And it's assigned its own texture, and you can vary that texture's resolution however you want. And this allowed them to get much more efficient high-resolution rendering. And that was kind of the idea that informed this. I was like, oh, okay, I want to be able to have different resolutions for face of the icosahedron in different ways. I don't know, it was surprisingly efficient. It worked quite well. Pixar has the right idea.
Yeah, by the way, they have an amazing book about how they come up with these ideas. If anybody read the book.
The Catmull book?
Catmull. Yeah, Creativity Inc. Beautiful book.
Yeah.
Mm-hmm.
I also think this kind of moves us a little bit more towards kind of ideas of sort of foveation as well. Yeah. So my academic background is in eye movements. So we, as biological ordinals, we definitely don't pay attention to 4 pi steradians. We only pay attention to a small amount, and there's a pipeline of, oh, there's something interesting over there. Okay, I'm going to dedicate more processing resources to that thing.
Yeah. Yeah, I was actually at a workshop at CVPR last year, and people were talking about spherical imaging, and somebody brought up exactly that, foveated images. And apparently, once upon a time, this was like a hot topic in vision. People played around with foveated images. I'm not too familiar with it, but I guess the idea was, try to mimic how the human eye worked.
I mean, there's a sort of biological inspiration, but I think from an engineering perspective, there's also very practical sort of application. I mean, in maritime autonomy, one of the things that we've done is to try to use the panoramic images to, cue a pan-tilt zoom camera onto a potential target, simply because it's just too expensive to get high enough resolution panoramic cameras that can do the job, and the amount of data is just too much.
Yeah. Yeah.
Go ahead.
Oh, sorry. I was just saying, I was literally having a conversation with a colleague of mine like last week about foveated object detection, and how I could see how, you could probably get, or we were talking about potential low power applications of foveated object detection, because you don't need to process the entire image. You can look at a subset of anchor boxes for like, your detectron or whatever, your mask CNN. And yeah, I could totally see some benefits for that. It's an interesting idea. It's a useful topic.
While we were talking, Jan Schmid here also posted an archive paper about optimization feature detection in CUDA. By the way, feel free also to post it in the subreddit. Maybe somebody else will use it. Yes. Anybody else? Any more questions before we wrap up? No? Okay. I have a couple of words, not a lot. Again, I'm going to be sending all the links to where you can find us. This, of course, this talk is recorded. And of course, this will be on YouTube. I have a feeling this is going to be a very interesting talk on our YouTube channel. You have the YouTube here already. I texted it in the chat, the newsletter there with all the updates when the recording will be up. The subreddit where if anybody had any interesting references, please post it there. I myself like having it there. It's a good archive also, and others look there. The Discord for instant messaging, that's where we, talk live and exchange ideas live. Mark, really, I feel like this Discord will be also interesting for you. I have a feeling. I will be posting references, or Mark will post, one of us will post references in the Reddit with everything we talked about, including data sets and the papers and everything. This is a good chance for me to say thank you again for everybody who were online, everybody who will be watching this recording. It's an awesome thing having people from all over the world discuss high-end stuff. And me personally, I get to learn from the, people who have much more knowledge than me and much more experience. So I get personal joy from it and personal fulfillment, and it helps me in my job. And I hope for others. And I love seeing these connections form, and I hope we can continue doing it with much more lectures to come. Good time for me to ask again, if anybody knows of somebody who's working on high-end research or high-end products in the space of computer vision, machine learning, anything to do with it, please let me know. I am lining up more lectures. They're still not published, but they will be soon. What else? We're almost at 1,000 people now within 3 months. This is amazing growth, amazing speed. I hope we can continue this, because the more people we have, the more easier it becomes to bring on lecturers. And yeah, thank you everybody. Really, thank you so much for the participation. Thank you, Mark, so much for the info. I will be contacting you after. I have a couple of more questions. Maybe we can have a Zoom call. There's a couple of cool stuff that you talked about that I wanna go back to. Yeah, that's it from me.
Awesome. Yeah, thank you all again. Appreciate it. Thanks for tuning in.
I will be the last one to log off, because when I log off, the screen closes for everyone. So bye, everybody.
Thank you very much, everyone.
Oops.